Good afternoon and welcome back to Codex. Our speaker today is Soledad Villar, who is an assistant professor at Johns Hopkins University. Soledad is known for using tools from optimization and invariant theory to tackle emerging problems in machine learning and data science. Today, she will tell us what happens when Galois theory and low-rank matrix completion meet equivariant machine learning. Take it away, Soledad.
Well, thank you for the introduction, and thank you for the invitation. I hope I do a good job. I haven't given a talk in a while. I'm going to talk about invariant machine learning and Galois theory. And this is joint work with my PhD student, Teresa Juan, my postdoc, Ben Bloom-Smith, and my collaborator at Apple, Marco Cuturi. So we're gonna introduce the topic first. And so as a motivation for this topic, and you've seen this slide before, we are thinking about symmetries arising in deep learning architectures. And symmetries are a very generic concept, and they appear often in things that maybe we don't think about them, but they are there. So for instance, in convolutional neural networks, there's some translation symmetry just in the definition of the models. Recurrent neural networks as well. Old school neural networks had symmetries. Graph neural networks are especially designed to have symmetries, to be aware of the permutation symmetry that arises from the fact that when you express a graph, the representation of the graph as a matrix is not unique. So if you write this graph in many ways, then they represent the same graph. And so if we're going to do machine learning on top of it, then we have to be consistent with the fact that there's not a unique representation. And also transformers can also be seen as having some permutation symmetries as well. And the idea of exploiting symmetries in machine learning is very widely accepted. And this is related with the topic of geometric deep learning, that the idea is to exploit the mathematical structure of the problems and of the objects that one works with, and just design methods that use this mathematical structure. So this is kind of like the theme that we are going to think about. And so in the physical sciences, we can think of two types of symmetries. The symmetries that are the passive symmetries are the ones that I just talked about with the graphs. The fact that there's not a unique representation, a unique mathematical representation of an object. So if we express the object in a different but equivalent way, then the machine learning models should be consistent with that change of representation. So you can think of it as a coordinate freedom, as units equivariance, as gauges invariance and equivariances. So that's like the biggest kind of symmetries that one can think about. And also in physics, there are other forms of symmetries that are more restrictive, that kind of like add a non-vacuous constraint on your problem that has to do with the symmetries that the physics law satisfies. So for instance, if you have a system that conserves energy, then there is a time translation symmetry in that system. Or conservation of momentum, there's also an equivalent symmetry, which is a space translation symmetry, and so on. And so these are the kind of symmetries that people think about when working on the natural sciences or the physical sciences. And the claim is that if we're going to do machine learning, then we should write methods that are consistent with these symmetries. And there's mathematical proofs showing that if you do that, then the sample complexity of the problems is smaller, and you can achieve a better generalization error with fewer samples and in a shortest time. And that's kind of intuitive because the problem is reduced. So the size of the problem is reduced by the symmetries that one implements. So in this talk, I'm just going to focus on two things, on point clouds and in symmetric matrices. And there's a lot of work in machine learning on point clouds from math, but also from computer vision. And there's a lot of papers out there doing machine learning on point clouds with several applications, including chemistry, astronomy, computer vision, etc. And so this is just like a slide showing latest works in machine learning on point clouds. And I'm just going to give a specific approach that just will focus on some mathematical tools that we can use to address this problem. But I'm not claiming that this is the best thing that you can do for point clouds. It's just to understand how these mathematical tools can be seen in the context of these problems. And so the motivating problem for me, when I started working on this, was in a problem in cosmology with Kate Story-Fisher, who finished her PhD at NYU a couple of years ago, and now she's a postdoc at Stanford. And in her PhD thesis, she was looking on some machine learning models for some problems in cosmology. So the idea is that she has in cosmology, there's like several forms of simulations of the universe. Some of them are very complicated, and some of them are simplifications of these complicated models. So the dark matter only models are the ones that just use gravity to model the evolution of the universe. And there's others that are more complicated that use hydrodynamics, so more complicated physics into the model. So one can run a very large dark matter only simulation, but you cannot run a very large hydrodynamics full simulation. So then what Kate wanted to do was to see if it was possible for her to do some form of regression where she had the point clouds from these dark matter only simulations, and she wanted to learn what properties she would have obtained had she been able to run the full hydrodynamic simulation on these point clouds. So basically, it's just a regression problem on point clouds, and that's what I'm going to think about now. Just the cosmology, that's for a different talk from a different person. So mathematically, the setting is the following. So we have a point cloud that we can represent as a matrix where each of the rows, each of the columns of the matrix are the coordinates of a point. So this is like a D times N matrix. That is my point cloud. And so this regression that I'm going to do, like learn what would have been the mass of this halo if I had run the full hydrodynamic simulation, then that regression problem is going to be invariant with respect to rotations of the point cloud, translations of the point cloud, and also permutations of the point in the point cloud. So all the points are exchangeable. So I want to look at rotations, translations, and permutations. Okay. Translations, rotations, and also reflections. Yeah. So the full OD, ED, which is like OD plus translations. So basically, I want to do a regression based on those that is invariant with respect to those symmetries. So the first thing that I can think about is how do you tackle translations of this point cloud? And the easiest way to do this, in my opinion, is to use this concept called canonicalization, which is basically if you have this group of translations, we're gonna fix like some frame, and then I'm going to see, like, we're going to translate all these possible point clouds to a fixed frame. So we're going to choose like one representative in the orbit of this group action. And this representative can be the one where the center of mass is equal to 0. And so if I do that, then I can just, given a point cloud, I translate it so that the center of mass is equal to 0. And then that gives me a way to learn a function that is invariant with respect to translations. And that you can do for many groups. And that is what it's called canonicalization. And there's many papers in machine learning that implement invariances or equivariances using this canonicalization technique, which is easy to do in translations, but for other group actions, it's not that easy to do. So here what I do is for each point, I subtract the center of mass, and then that gives me one representative, the template, the representative of this point cloud for this group action. Yeah. So that's that. So that kind of like solves the translation problems. And then we have rotations, reflections, and permutation. So for rotations and reflections, which is basically the orthogonal group, I'm gonna use a classical the classical invariant theory, the first fundamental theorem for invariant theory that tells me that if I have a function that is invariant with respect to the orthogonal group, meaning that if I apply the same orthogonal transformation to each of the inputs, the function doesn't change. Then this function is OD invariant if and only if I can write it as a function of the inner products of the inputs. Right, so then a function that takes n vectors in Rd, which is our point cloud, and outputs a scalar, is invariant if and only if I can write it as a function of the inner products. And so we can think of it as we have n points in Rd, and then we can construct these features, which is an n by n matrix of the matrix of inner products, and then any function that is invariant factors through this feature space. So it's easy to see that that's the case, because if you have your point cloud and you construct all the inner products, then if you rotate your point cloud, the inner products don't change. So that would make it so that it's invariant. The question is like if all invariant functions can be written this way, and that's something that is basically the first fundamental theorem of invariant theory. But you can, there's many ways to see that using like matrix factorization, for instance. And then there's similar characterizations for other group actions, like the Lorentz group, the rotations, which is that it gives you something a little bit more complicated. I can talk about it if you're interested, symplectic group, unitary groups, etc. But let's focus on this cosmology problem. So we only had the invariant functions with respect to rotations, reflections, and translations, which we have already done. And now we are going to go to the permutations, which is the part that I haven't talked about yet. So I think that in my previous talk and codex, I talked about this already, but this part is the permutations part, which is the thing that I haven't talked about in codex yet. So the idea is the following. We have the matrix corresponding to the points. And so now we are acting by rotations and reflections on the left. So multiplying by a matrix NOD on the left, and then permuting the columns on the right. So then just multiplying by a permutation matrix on the right of this V. And so we know from the previous slide that a function from this point cloud to R is OD invariant if and only if you can write it as a function of the Gram matrix. And now we want to see what happens with the permutations. So then now, if I apply a permutation to my V, then f of V is going to be f tilde of the inner products of these permuted V's. And so basically the action of permutations on the point cloud translates on an action of permutations by conjugation on the Gram matrix, right? Because I multiply by the permutation on the right, and then when I compute the Gram matrix, then the permutation transpose appears on the left. So that now I have an invariant function with respect to permutations acting by conjugation, which you can think of it as if I write the Gram matrix, the action of permutation by conjugations corresponds to permuting the rows and the columns by the same permutation, by the same permutation matrix, or the same permutation object. And so this is the symmetry that appears in graph neural networks, right? The graph neural networks that I talked about earlier, which a lot of, like here we have experts on graph neural networks like Michael, you can see that this is the symmetry that appears in graph neural networks, and graph neural networks are designed to be invariant or equivariant with respect to this symmetry. But I'm not going to use graph neural networks. I'm going to give you an alternative thing. And the reason, there's one reason or a few reasons why I'm not going to use graph neural networks. Let's see if it convinces you or not. But I'm going to show you an alternative thing that does not use graph neural networks. And why am I going to use this invariant theory or Galois theory instead of graph neural networks? Well, one reason is that constructing the graph has O of n squared complexity, and we'll be able to learn invariance with O of n times d complexity. So we're not going to be needing to write the entire Gram matrix. And we think that we have improved expressivity over vanilla message passing neural networks. We don't have a formal statement of that, but we can discuss that. And then there are interesting mathematical tools that could be potentially used more broadly, and I'm going to tell you how to use these tools. So the tools that I'm going to use are basically Galois theory. So the idea is the following. So we are interested in the permutation group acting by conjugation on these gram matrices. So basically permuting the rows and columns. And now I'm going to say, well, I don't know how to write the invariance for this group, but I'm going to say, well, this group, this group acting in this way, you can think of it as a subgroup of a larger group, which is the group of permutations of n elements times the permutation of n choose 2 elements, that basically acts by permuting a diagonal element to a diagonal element and an off diagonal to an off diagonal element. So basically, if I permute rows and columns of my original matrix, then any diagonal element goes to another diagonal element, and any off diagonal element goes to another off diagonal element. But it's not that any permutation of this form corresponds to a permutation of this form, right? Because I can do this permutation of independently permuting diagonal to diagonal and off diagonal to off diagonal in a way that is inconsistent with the original permutation of rows and columns, right? But so basically, this group is a bigger group that inside it has the group that acts in the way that I want it to act. Does that make sense? More or less.
So I have a question.
Yes.
Is this related to Galois theory somehow?
It's going to be related to Galois theory in the next slide. Yes.
Oh, cool. Thanks.
Yeah, it's just like, yeah, not Galois theory yet. But basically, I'm considering like a group, like a subgroup, and then this subgroup will correspond to a field extension, and that's where the Galois theory is going to come up. Right? Does that make sense? So basically, I'm just setting up like the groups. Yeah. Maybe I should call this setup. Just not Galois theory yet, but this is the setup. Okay, great. And so now here we are going to have the field extension. So if F is invariant with respect to the permutations acting in this form, then since this is a group, this is a subgroup, then Sn is a subgroup of this bigger thing. So the invariants with respect to this action are larger than the invariance with respect to this action. So you have more invariance with respect to this than invariance with respect to that, just because it's a smaller group, so it fixes more things, right? And so we have the invariance with respect to the first action, and those include the invariance with respect to the action by the larger group. So the invariance with respect to the action by a larger group are very easy to know because it's just a polynomial that sends a diagonal to a diagonal and an off diagonal to an off diagonal. So that is just like the elementary symmetric polynomials on the diagonals and the elementary symmetric polynomials on the off diagonals, and that's it. Does that make sense? Right. So basically what we want to know is what are the invariants with respect to the group that we care about, which is the group, the Sn acting by conjugation. Right. And so we're going to use Galois theory to that basically informally in this context will say that if we construct a set of invariant polynomials that are only fixed by the desired group, which is the smaller group, and with that mean that no other bigger group fixes all these invariants. So maybe some of them are invariant with respect to a bigger group, but there's no bigger group that fixes all of them at the same time. Then those invariants generate the field of invariant functions. That's what we are going to use about Galois theory. And then there's a theorem by Rosenschmidt in the 1950s that says that the orbits that the field generators fail to uniquely identify, has to satisfy a finite set of polynomial equations, and therefore they're a zero measure set, an invariant, closed invariant zero measure set. So basically what we're going to do is we're going to construct a set of invariants that are only fixed by Sn acting by conjugation. And then those invariants are going to generate the field of invariant functions. And then with those invariants, we can universally approximate any invariant function outside a bad set, which is an algebraic invariant closed set.
Soledad, is there a, like, presumably you need more than just that they're only fixed by the desired group, because once I could just have a single function that does this, right? And presumably that's not enough to generate.
That are only fixed by the group that I want, and by no other bigger group.
So I just need a single function that does that, and then I'm good.
Yes, if
Wow.
if it satisfies that, then yes.
Great, thank you.
That's like the minimal, like the, what is it called? It has a name in algebra, like the minimum generating object, something like that.
But can I just clarify that? So
Yeah.
like maybe I'd get lucky and it would just happen with one, but maybe I need 3 or 4, and like maybe each of those 3 or 4, one by one, there's a bigger group that would fix it. But to get all 3 or 4 of them, I would intersect all those big groups. And then is that what we're talking about? Like I have a set of functions, and if I take the intersection of all of the groups that fix them, that intersection is my smaller group. That's
Yeah,
what I want.
true. Yes.
Okay. Cool. Thank you.
Yeah.
Thank you. Awesome.
There's a theorem that tells you that under some assumptions, a field extension is given by an only element, and I think that we satisfy that the assumptions of that theorem here. So it would be that we only need one element. Yeah. So here we have our tower of groups, and here we have our tower of fields. And well, here actually, these are tower of fields. So we start with the polynomials on entries of the symmetric matrix. So just the entries xij, which is like n choose 2 because the matrix is symmetric. And these polynomials are fixed by the identity group, just because this is our base field. And then we can consider the large group, which is the field and which corresponds to the field of invariant functions that permutes diagonal elements to diagonal elements and off diagonal elements to off diagonal elements. And we know that this field is generated by the symmetric polynomials on the diagonal elements and the symmetric polynomials on the off diagonal elements. And then we're going to consider a field extension so that it is only fixed like by this group acting by conjugation. And then in order to do that, we only need to add this element, which I should have called, actually I should have called R here. And this is no. And this element that we add is a polynomial that basically what it does is that it does the tying that the permutation of the diagonal element to the diagonal element and the off diagonal element to the off diagonal element is tied. So it's consistent. So that's something that can be shown, that if you add this polynomial, then this ties the permutation of the diagonal to diagonal and the off diagonal to off diagonal, and the field of invariant functions by conjugation is generated by these polynomials that we have below, and then this extra element, extra polynomial that ties that diagonal to diagonal and off diagonal to off diagonal. And therefore, the field generated by this is the field of invariant functions that is invariant with respect to the action of permutations by conjugation. That is the idea. And so that is the idea of how you construct these invariants. And then there is more work needed to show that, for instance, this bad set that I mentioned, that is where this approximation may fail, which is like, you can think of it as this field this is a field. It's not, these are field generators, they're not algebra generators. So everything that is invariant can be written as a quotient of polynomials. So when the polynomial in the denominator is equal to 0, then this quotient is not well defined. So in those cases, this is where we may not be able to express everything. And so these are the things that may not be expressed. And these are the bad set, the zero measure set. But if we restrict ourselves to point clouds, where we're looking at low rank matrices, then we don't know. The low rank matrices are already measure 0. So we don't know whether this measure 0 set intersects in a measure 0 way in this thing that is also measure 0. So that's why we need more work to extend this thing to point clouds. And but it actually works for point clouds as well. So the statement is also true for point clouds.
So I'm sorry, can I interrupt?
Yeah.
I just want to clarify, because I think you just said something I didn't understand before. When you say invariant function, are you talking about rational functions? Specifically rational functions? Are any of your functions ever not polynomial over another polynomial?
Yes. So for here we look at rational functions for the definition of the invariants, but then you can use some like Stone-Weierstrass like theorems to extend it to continuous functions.
Okay. Okay, thank you.
But these objects, yeah, are rational functions. Yeah.
Cool. Okay,
Yeah.
thanks.
Good. And that's something that is done a lot in machine learning. They use like Stone-Weierstrass to prove universality of these invariant or not invariant architectures. Yeah. Good point. But in practice, so this is what the theory tells you, but in practice, we are not going to implement it like that. We're not going to use polynomials. We're going to do a DeepSets trick. Are you familiar with DeepSets? DeepSets is like a very, very cool thing. So there's this paper called DeepSets from Zahir and collaborators from 2019 that has like thousands of citations. And basically basically they propose an invariant machine learning method, which is based on the following. But it's just permutation invariant. So the idea is that if you have a function that say has an input that in our case is like rk by n, and the output is rs. So here the action of permutations is on the right, but it doesn't matter. You can write it in any form. And then if you have a function f like that is invariant, then you can write it as the composition of, or you can approximate it actually by the composition of two functions. One is like a feature map that takes any of your inputs here and maps it to another higher dimensional space, RL here. And then the other one, which is like an aggregation map that takes a vector in RL and then goes to the output space. And so you can write a function of this form as or you can approximate a function of this form as the aggregation of the sum over the columns of the application of the same phi. So you apply the same phi to each of the columns of your original matrix, and then you aggregate the solution by just taking an average or summing and then applying another function. That gives you like the architecture of a permutation invariant function. And so the way this is proven in the original paper in the DeepSets is using symmetric polynomials. So it's going to a very high dimensional space, because if you want to generate the symmetric polynomials in dimension k times n, then you have to go to a very larger space. But then there's a recent paper that uses ideas of actually, like, I think compressed sensing, but I'm not 100% sure, that show that you can reduce the dimension of the embedding to something like 2 times k times n, and you still can approximate with that. You can be universally approximating by reducing the size of the embedding. And this is a paper by Tabagi and Wang from like a couple of years ago, maybe last year. So this is a very nice way to write your invariant functions, because first note that this formulation is independent of n. So this is a sum over all columns and it's independent of n. So the parameters that your model requires is independent of n. And then sure, if you want to be universal approximating, then sure, you need to grow your model with n. But if you don't care about being universally approximating, then you can write a model that trains on objects of size 100 or like 100 elements in your point cloud, and then evaluate it in point clouds that had 2000. Because the model is defined in a way that you can apply it on objects of different sizes. And that's super useful for machine learning. When you work with invariant polynomials, that's not the case. Like when you work with elementary symmetric polynomials, yeah, you need to have a fixed size of input. So that's a very nice property of this. And so basically the architecture that we propose in this paper, based on the theory that we had before, plus this DeepSets idea, is the following. So you start with an X, which is a symmetric matrix, n by n symmetric matrix, and then your invariant function is going to be defined as a function of the DeepSets architecture applied to your diagonal entries, a DeepSets architecture applied to the off-diagonal entries, and then the F star, which is the thing that glues together the diagonal with the off-diagonal that comes from this Galois theory. And then we can prove that this function F, written in this form, can universally approximate invariant functions on symmetric matrices outside this invariant closed zero measure bad set that comes from this Rosenschmidt theorem. So far, so good. Good. So here we have O of n squared features still. I'm going to show you how you can go from these O of n squared features to O of n times d features. But here I'm not going to use Galois theory. I'm just going to use some ideas from some of your collaborators on low rank matrix completion. So the idea is the following. And actually, this idea, Dustin gave me this idea in Paris last year. So the idea is the following. We have this point cloud that has d rows and n columns. So each point is a column of this matrix. And so what I'm going to do is, and I want to find a function that is invariant with respect to permutations and rotations. Okay. So what I'm going to do is I'm going to consider a matrix of centers. And these centers, C of V, are going to be K centers. And these centers need to be OD equivariant. So if I rotate my point cloud, the centers rotate as well. And they have to be invariant with respect to permutations. And the way I can think of the centers to be invariant with respect to permutations is like, if I can, for instance, if K is small, what I can do is I take my centers and say a K means centroids, and then I order them by 2 norm. And so if given my point cloud, I do a rotation, the points, the centers rotate, but the 2 norm doesn't change. So if I order the centers, and K means the order of the centers is arbitrary, but if I order them by 2 norm, then I have a kind of like a unique identification of each of the centers, so I can put them in the right order. So this is kind of like a form of canonicalization of the centers, like a way to write them uniquely with respect to the action of permutations, which I can do for the centers because they're few, but presumably I could do it for the point cloud as well, but that wouldn't make sense because the point cloud is very large. And also that would make something that is completely unstable with respect to noise. Whereas the centers, it would be something that is more stable, I argue. Okay, so I have these centers that are OD equivariant and invariant with respect to permutations. And so I consider this augmented matrix that has first the points and then the centers. And I consider the gram matrix of this matrix. And this gram matrix here can be reconstructed. This is a rank D matrix. Can be reconstructed by a D rows or columns. This is symmetric, so it doesn't matter. So I can reconstruct this matrix X tilde from, say, the last D rows of this matrix. And that's what I use this low rank matrix completion idea. And so I can feed my machine learning model just this part of the matrix, and I can get something that is invariant with respect to permutations and OD invariant, just because given this, there exists a unique reconstruction of the entire matrix. And so here I take K equals to D, and I do that. So the way I would define an invariant machine learning model with all of ND features would be the following. I take my my D times N matrix of points, then I construct this C as defined above, the matrix of the centers, and then I do a DeepSets model on this C transpose B. And so this is D times N. So the deep set is with respect to the N, the points, but the D's are ordered, and the coordinates are ordered with respect to the canonicalization of the centers that I just did. And then this matrix of inner products of the centers themselves, which is basically that. So since the reconstruction of the original matrix is unique from this matrix, then information theoretically, you can know that if you feed a model from here, then it's equivalent to feed the model from the entire thing. And so basically that's the way you define it. So what you can prove from this model is this machine learning model based on this like low rank matrix completion, uniqueness, can universally approximate invariant functions on point clouds outside an invariant closed zero measure set. And this, the size of this model is like O of ND plus D squared. So that's that. any questions about this? Did it make sense, more or less?
I did have a question. So the sorting the two norms, or sorry, sorting the centers by two norm, seems like it would be an unstable process. Is that an issue? Is that something we should be worried about?
I think it's not unstable. It's these centers, and these centers you can construct them using k-means. So the k-means solution has there's like an open set where the solution, which each point is assigned to the same cluster, and the center would be stable would be continuous in that open set that has full measure. There may be other ways to define the centers in a stable way, but if you do it with k-means, that works. Does that make sense?
Yeah, I think it does. Thanks.
So there is like when points go from one cluster to the other one, that's where the centers can become unstable. But this is continuous outside that. Okay, so the next thing that I can share with you is that we have numerical experiments showing that this performs reasonably well on some problems. So one problem that we consider is this molecular prediction on QM7B, which is like a standard benchmark for invariant machine learning. And basically here, each molecule is represented by an n by n symmetric matrix, and the regression is invariant with respect to the permutation of the rows and the columns in this matrix. So it's kind of like the first thing that I show you. And for here, and here we use a model that is an MLP of the DeepSets of the diagonal, the off diagonal, and the extra element, and then we show that it performs comparably with like the state of the art. And another problem that we consider is now in point clouds is this model net 10, which is point clouds that represent furniture. And what we designed as a goal for this learning problem is to learn this Gromov-Wasserstein lower bound that actually was implemented by Dan Packer in this ODT JAX model. He implemented this Gromov-Wasserstein lower bound, and we say, well, can we learn to predict this lower bound of the Gromov-Wasserstein based on these point clouds? And that basically was the learning task that we designed, and it worked reasonably well. These are just toys, I would say. The idea or the interesting thing that we want to apply it to is this like cosmology problems, but we haven't done that yet. I think that's a very interesting problem. And so I will conclude with like a final set of remarks, and then if I have time, I can tell you a little bit about what is an interesting open problem that I haven't figured out yet. So what we did was we used we wanted to write invariant functions on point clouds via invariant features. We used Galois theory to give us generic universality on symmetric matrices. We use tricks from low-rank matrix completion and DeepSets to give an information theoretically optimal complexity for point clouds. And in future work, sure, apply these ideas to cosmology. I'm also interested in thinking about like how this Galois theory can be used in machine learning, and what is the connection with the Stone-Weierstrass ideas that people use for this approximation, the universality claims in machine learning. And also the extension to equivariant functions. And this is where if I have time, I can tell you a little bit more. Okay, I'll start 5 minutes at most. So the idea is the following. We did everything for invariant functions, but sometimes we care about equivariant functions, which is like if I act by a group element in the input, maybe I act by a group element in the output, maybe with a different representation or with the same representation, but say that is the same. So a classical thing that one can think of is I already show you how we can do invariant functions with respect to OD using the first fundamental theorem for OD that tells you that a function is invariant if and only if you can write it as a function of the inner products of the inputs. And we can ask a function that takes n vectors in Rd and outputs a vector in Rd. This function is OD equivariant. So basically like h of b, like r b1, r bn is equal to r h of b1 bn. If and only if, and this is something that is not too hard to prove, you can write it as a linear combination of the input vectors. So this is an input vector, and the coefficient functions need to be invariant with respect to need to be invariant with respect to the action of OD. So you can write this as a linear combination of the input vectors and the coefficients are invariant. So basically functions of the inner products. And that is something that is not very hard to prove. The idea is that if I have a function h that is equivariant, so h of h from Rd to the n to Rd is equivariant, then the function f that goes from Rd to the n times Rd to R is invariant when I define the function f to be f of b1, bn, b star to be the inner product between h of b1, bn, and b star. So you can see that if I write my function f in this form, since this is equivariant and b star is also equivariant, it's just identity, then this is going to be invariant. So if this is invariant, then I can write this as a function of the inner products. So this is going to be a function of the inner products of b1, or maybe I should write with the same notation as before, like bi transpose bj and bs transpose b star, where I, j, s go from 1 to n, right? But since this matrix, since this function over here is linear in b star, then whatever function I have here needs to be linear in b star as well. So this function is going to be a sum of some fs tilde of bi transpose bj, and this is unconstrained, times bs b star. And then if now here, if I take the derivative with respect to b star on both sides, then I get that h of b1, bn is equal to a sum of this fs bi transpose bj times bs. Right, that's the proof. And I think that I already did this proof last year when I gave this talk at Codex. So basically this tells you that knowing the invariant functions allows you to write the equivariant functions, right? However, the invariant functions that I use to recover the equivariant functions are very specific invariant functions. They are invariant, but they are linear on the second entry, right? So basically what I say here is that the knowledge of the invariant maps on B times W star, where W star is just the dual of W, to R allows me to know what are the equivariant maps from B to W. And then the construction is basically taking the inner product, right? So I say, if H from B to W is equivariant, then I construct F that takes a V and an element of the dual of L, and then it outputs L of F of B, basically. That's what I did in the previous slide. And this function is invariant. So, and then the construction goes the following. So if I have this function that is invariant and is linear with respect to the second thing, then when I take the derivative of this F with respect to the second thing, I obtain something that does not depend on W in the input because it was linear. And then it gives me something that goes from B to the W star star, which is equal to W, that is equivariant. And all the equivariant functions can be obtained this way. So what I did before in this construction with these Galois features gave me some invariants, but these invariants are not linear because they're quotients of polynomials. So can I use these ideas that I have here presenting, or maybe other ideas, but can I use the invariants that I constructed at the beginning of the talk using the Galois theory to produce equivariant functions? And that's what I don't know if I can do. But basically, that's the open question that I wanted to leave at the end. So can we do something similar with the invariants from Galois theory to produce equivariant functions? And with that, this is just the algorithm that goes from invariance to equivariance that use the fact that I have generators of the ring of invariant functions. So now I don't have a field. I have algebra generators, not that everything can be written as product and sums of these, not quotients. And so if I take the ones that are degree 0 in W star, and I take the ones that are degree 1 in W star, then with these ones, I can construct and discard the rest. I can construct the invariant functions, but by basically taking the derivatives of these guys with respect to the second coordinate and then multiply them by just basis elements. Yeah, so I take these ones. These ones are the corresponding to like the derivatives of the degree 1 polynomials times the degree 0 polynomials, which were the invariants. So if we see here in this formulation here, these guys are the derivatives of the degree 1 polynomials that are invariant, and these ones are the degree 0 polynomials that are invariant. And this is what we get. Anyway, so that's just like maybe an interesting open problem to think about. And so these are my references, and I'm happy to take questions now.
Right. Thanks so
Thank
much,
you.
Soledad. Dustin?